Good morning, everyone, and good morning, Uday. It's a great pleasure and honor for me to have Professor Uday here uh, to give a talk on MLIR in this session. So Professor Uday is an accomplished researcher in compilers, did lots of nice work in polyhedral compilation and in many other areas of compilers. So welcome, Uday. So again, so we're all very happy to have you here in today's session. Yeah.
Yes, so thank you, Suresh. So, yeah, I'm pleased to give this lecture here as part of your course lecture series. Could you just let me know if it's, so this is planned for about an hour or 45 minutes plus hour? How long is it going to
Hour is good.
1 hour, right? I
One.
think with questions.
Yeah, sure.
Right, so that is including questions. Okay,
Yeah.
so please feel free to ask me questions. As Suresh mentioned, I'm Uday. I'm a faculty member at the Institute of Science. And so this talk is on MLIR, multi-level intermediate representation, which is a compiler intermediate representation. So as such, this talk is on uh, the area of compilers and compiler infrastructure and using compilers for high performance computing and as well as for productivity. Right? Okay, so I'll start with some background. I know that many of you are already familiar with compilers, but it's good to take a look at how compilers evolved, some of the history there, and the challenges that we are facing today. So here a lot is about compiler infrastructure. So compiler infrastructure is different from compiler as such. Since using compiler infrastructure, you can build many compilers. So using the same, for example, GCC infrastructure supports multiple languages, C, C++, Fortran, Objective-C. So with one compiler infrastructure, you can build N compilers, support many languages. Right? So similarly, LLVM mentioned about is a compiler infrastructure. So this talk is most about compiler infrastructures, not about a specific compiler. Okay, so let's see how compilers evolved. So in the 1970s, 80s, at the time when uh, there was no open source, no internet, uh, no such a sharing of code, and so on. People, whenever there was a new language, there were these languages, and then people came up with compilers for those for the new hardware. So on the left, I have languages, and on the right, I have targets. It targets as in hardware. Each time you have a new hardware, and then you have a new language, you build a compiler from that language to that target, right? And if you take this sort of an approach, right? If you have M languages on the left and N targets on the right, you'll ultimately get M times N compilers. So it's not a scalable approach. You get this for every language, you would have to support all the different targets. And people saw that this is not a scalable way. So even at a single company like IBM, right, they wanted to, although there was no internet open source, over there, they wanted to share this code and infrastructure that each time you have a new hardware, you don't have to build N or M compilers. We want to reuse things as much as possible. So that's why compilers evolved to become this, which is a figure that a lot of textbooks will show you. Instead of building M times and compilers, one for each language and multiple for different language, you have an intermediate representation. And what happens is you have an intermediate representation that is language neutral and that is hardware neutral, and you build all your optimizations on that intermediate representation, and then you have a backend for each hardware. So each time you have a new language, you just have to create a front end, and each time you have a new hardware, you have to create a new backend. As such, you are going to have uh, instead of m times n, you get m plus n plus 1 compilers. So m front ends, n back ends, and the 1 is the thing in between, which is a bigger, more complex thing. As such, from m times n, you go to m plus n plus 1, which is a a big leap in reusability. Right? So this is what most textbooks show, but the reality today is actually different. It's even better than this, especially with some of with the state-of-the-art infrastructures. So let's see how modern compilers look. Now this is LLVM, which has been tremendously successful. This is the go-to infrastructure for to support new hardware. People build a backend for LLVM, new languages. They use LLVM for their compilation and lowering. And it gets even better in the sense LLVM reuses a lot of infrastructure even across backends. So when you have something a new backend, you don't have to uh, redo a lot of the stuff, but you just say, here are my registers and here's my set of instructions, here are the rewrite rules, and they have a lot of automatic generation infrastructure, right? Or they have a framework through which they can deal with things like instruction selection, have the instruction scheduling, register allocation. So of course, you have to do something new for each backend, but adding a new backend is not, you do share infrastructure even across the backends. Right? The instruction selection infrastructure, rewrite rules, and so on are all shared across different. So that's why I say small n, not capital N, because uh, two times the number of backends is not two times the effort. There is some common stuff, right? So they're trying to share as much as possible, even on the across the backends, the common infrastructure. And front ends, obviously, you need a front end to lower to. That's the term we use, lowering. Right? You go from a higher level representation to lower representation, and so you low. That's called lowering. And then you would lower to LLVM and then you have a lot of infrastructure on the LLVM. So whenever people say LLVM, you think of it as one compiler, but LLVM is not a compiler, but it's a compiler infrastructure. The compiler is actually a Clang, typically in that ecosystem, which Clang lowers to LLVM. For Clang is the compiler for C, C++, Objective C, which basically lowers LLVMs. But the whole compiler is actually called Clang, not LLVM, but it uses LLVM infrastructure. So this is LLVM. Inside it has a LLVM IR. There are multiple representation again within that. Although it's a single IR, they have a machine IR, LLVM IR, and there are other things like selection DAG, different representation in between. But overall, it's one compiler infrastructure that is currently serving a lot of the languages that you use today. Right? A lot of statically typed languages: C, C++, Objective C, Rust, Swift, Julia, TensorFlow, and many other things, including domain-specific languages. Behind the scenes, you may not know, but they actually load LLVM. Even other things like on the phones, Apple uses LLVM for its, I believe, some of the graphics pipelines, and so under the hood, a lot of things that we see today are happening through LLVM. Now, LLVM is not the only infrastructure. There's also GCC, but GCC is not known to be as modular and reusable. So LLVM has become the preferred choice, whether it's for academic research, for industry, because it's so easy to uh, build things and get started with LLVM because of its modular design. And so for the future, people are just using LLVM, as although GCC supports many things. Linux kernel still does not compile with LLVM. So GCC, in terms of the number of backends and things it supports, is much larger. LLVM is still not there, but it is it's what is being used for all the future projects, academic research, uh, and for people to collaborate on, and for any of the new hardware that's coming up. Okay, any questions so far?
I think we are good, like so far.
Okay, so let's again recall the picture that I showed, M times N, where you have M language and targets, and everyone is trying to build the compiler, and this lot of duplication of effort, right? So let's fast forward to 2020 now, right, or even 2010, where programming models are becoming more and more high level. It's not C, C++, Fortran are not the only things that people are using. People are using very high level abstractions, high level languages, programming models. Some are based on Python, TensorFlow, PyTorch. New domains have new programming models. And it turns out that LLVM is too low level to deal with those programming models. And I'll just explain that in a little bit more detail. These languages or these programming models have abstractions that are quite high level, and LLVM provides a low level representation. So these arrows that you see here going from here to here is a big jump in the abstraction, right? So it's a These are operating at the graph level, high level multi-dimensional array swiftness, where the LVM is quite low level. So especially if you look at MLAI, the MLAI domain, which is quite important and relevant today, LLVM is not, you can still do compilation with LLVM, but it's a sort of too low. It does not provide you the opportunity to implement transformations and optimizations in a convenient manner, right? So we are back to the same issue that we had in the 70s and 80s. On the left, I have again an explosion of all these new high-level programming models, TensorFlow, PyTorch, Keras, Swift, all kinds of languages without different abstractions. On the right side, we have explosion of ML and AI accelerators, CPUs, GPUs, specialized chips, and so on. And everyone's looking for the right compiler infrastructure so that you don't run into the M times N problem, right? And why not use LLVM? Just like I mentioned, it's a too low level. As a result, everyone is, since it's inadequate, they are implementing their own intermediate representation. And in that process, there's a duplication, and we're back to the 10 times n scenario. Okay, at least they may lower to LLVM and get a common backend, but everyone is implementing an intermediate representation to do the same thing in different ways. So as such, these green boxes that you see, it's a C, C++ compilation. The Clang uses a AST, Clang AST, which is lower to LLVM. Different languages, depending on the features that they have their own representation before they load LLVM. So Rust has HIR, Swift has SIL, uh, and typically these things are connected to the language, right? So there's not much to share between, let's say, SIL and Clang AST. So at some point they have to be different, but this big jump that is there in abstractions means that a lot of information is thrown away and you want something common, right? So for example, XLA, HLO, if there was the right representation, they could have just reused and shared that with the other things that are also building machine learning programming models. However, they have to invent their own box, and again, there is a lot of duplication and replication. So we're back to that problem. And so MLIR is, so this issue leads to a proliferation of new IRs, right? Everyone is building their own IR, intermediate representation, and I call this both horizontal and vertical proliferation. What this means is that uh, because a single IR is not equipped to deal with equipped to deal with the compilation starting from a high level to low level, people invent new IRs, and so within a single pipeline, there may be multiple IRs. So there may be a high level IR, then you lower it to a low level IR, and then and so on. So sometimes it will be two, three different. That's like what I call horizontal proliferation. So for example, TensorFlow itself uses so many different IRs within its system, right? For a specific TensorFlow and for a specific hardware, it goes as many because there is no single IR that can meet the needs of its compilers. So that's the horizontal proliferation. Lots of IRs from high level to low level, right? And each IR gets its own infrastructure. People have to be familiar with the code, the patterns, and it's not a it's in terms of engineering costs, it's quite it's not that great. So and then there's a vertical proliferation. That is, for every program model, they're building their own IR. So Intel has ngraph, TensorFlow, is PyTorch, the different languages, right? They're all building uh, different IRs, which are all similar in capability. They have the same kind of optimizations, dead code elimination, constant propagation, but just on higher level, and there's no reuse. So you have a proliferation of this IRs, and so this leads to duplication of infrastructure. Even within a single company, it would lead to, in the industry, let's say, it lead to engineering costs, make it harder for academia to collaborate. You're doing your own thing, others are doing their, and they're duplicating the same thing in different ways. There's also, importantly, phase ordering issue with the horizontal proliferation of IRs. That is, if you have this, for example, chain TF graph def, so on. So for many representations, till you get to a lower level, because they're using different representations, there's a phase ordering issue in the optimizations. That is, if you do some optimization now, later on, there's another optimization that somehow interacts with this optimization, and you want to customize the previous optimization for this one, so that it does the right thing. But you're already in two different representations, and so you cannot unify things because you've gone from one IR to another IR and so on until you get to the low level, and you have a phase ordering issue. Which one will you do first? And you cannot unify because they're again working on two different representations. However, if you had a single representation throughout, right, then you can move things around much more easily. Otherwise, you have to implement the same thing on this different IRs within your single pipeline. That's the phase ordering issue. There is loss of information at boundaries. You go from one IR to another, you throw a lot of information that to recover it, it's again hard. right? So you may try to do more and more just before lowering, and that makes things less modular. Right? And then obviously there's also the question inconsistent development patterns. Different IaaS will use different infrastructure conventions, and it is not that productive, right? If you have multiple IR. So I think the point I'm trying to make is having one IR, right? You can build n compilers, but if you have just one IR, you can save a lot. So that's where, coming back to this picture, everyone was looking for the right infrastructure, and that's where MLIR came in. And MLIR is basically trying to solve this problem. Right? That is, it's providing an intermediate representation that you can use, that is designed to be a principled intermediate representation that can serve the needs of various programming models: high level, low level, general purpose, domain specific. By domain specific, I mean, let's say some specific to image processing domain, some specific to a machine learning domain, or you want to build a new DSL, so that the same infrastructure is used, let's say for C++ compilation, the same thing is used for high level DSL. And what does an IR need to have to serve all of these needs properly, right? In a way that is convenient, that's key. So that's, and so it's trying to be the LLVM of the machine learning world also. So ML, I'll talk about it, stands for multi-level, but it is mainly been designed, uh, to start from, mainly been designed, especially the abstractions that are already available, to serve the needs of the ML AI programming models. Right? It can be completely general purpose, can be used for C, Fortran, low level code also, but it's especially focused. It's meant to have the abstractions needed for the machine learning programming models and deep learning models and so on. And so it's meant to, it's again goal, its goal is to solve the m times and m% problem but for the machine learning world and for the future generation of programming models and languages. Right? Of course, this is not the only solution. There are many competing solutions, like there is TVM, other people have Onyx. So ultimately, there's one or two maybe representations that will win. We need to see which one. Right? It's too early to say that this will be the only thing that everyone will switch to. But looks like that's where things are going. Any questions so far? Okay, so MLR was open source in April 2019, so it's just been a year. It's new, it's a brand new infrastructure, a lot of active development happening, which is why it's also interesting. If you're looking at making contributions to MLIR or doing innovative work that can have impact, so the ML stands for multi-level. It stands for many things. It's the to be accepted, the commonly used or the official expansion multi-level intermediate representation, because it provides you a way to represent IR at multiple levels through the same representation. Also called, because it's target machine learning, so that's why the ML was also chosen. Multidimensional loops was a key thing that was that distinguishes MLR from other IR. So ML could also start from multidimensional loop IR. It's also going to start from mid-level IR initially, because there was low level LLVM was already there, and high level people had lots of things, but the mid level one was what was lacking in LLVM and a lot of the IRs, and that was one of the significant contributions. So initially started calling it mid level IR, but eventually became multi-level IR. And MLR has first class abstractions for multidimensional arrays and loopness. So this is something LLVM does not have. That's one of the key things, but there are many new things in MLR. Right? So let's see. As I mentioned, it's able to represent code at multiple levels in a unified way. It has a fully round-trippable textual format. That is, it is not just an in-memory thing. You can dump MLR to text, and that will have all the information that was there in memory. So, and then if you read the parse the text back, so the MLR itself has a parser. You can parse MLR just like you can parse, and then construct the intermediate representation back in memory. So if you dump it and then parse it back, you won't lose any information. So everything that's there is part of the thing that you printed. And so if you send your file to your friend and then other than repeat it, they'll be able to see everything that you had. There's nothing sort of missing in the textual format. So if you print it and then pass it back, you get the same, semantically the same thing with no information loss or no information added. Progressive lowering, which is quite key if you go from very high level, something like a compute graph in TensorFlow, where you're doing operation on tensors and matrices to lower level instructions. It is able to represent all of them. Right? It has a way to represent all of them using the same representation without needing any other new representation. And the other more important thing is it's very flexible, extensible. You can, if the operations level do not satisfy any, There's a lot of infrastructure to allow you to easily add new dialects, what we will call, and basically build the thing that you need. So that's why it's expensive. That's what allows it to handle various domains and domain-specific compilation. So this figure actually is just a summary of MLIR. It shows the sort of a high level form, how you can model something high level, something mid level, and something low level in MLIR. These are not the only levels. These are not the only ways. But just if you classify the level of the IR, which form it is in, into three, these are the three. So the first one that I show on the top is like a high level form. Typically, that's how the code or IR will look like. Mid level form is mostly loops, and the low level form is mostly operations that are closer to the hardware. So you'll see, and the IR goes through these stages. So you'll start from something on the top, expand out to loop level form, and then further get rid of loops, and then you'll get branch and conditionals, and so on. And you get a low level form that is closer to your hardware. Right? So on the first, on the top, I have, you will see these are all operations. Whatever you see in brownish color, they're the operations. They take inputs and they give you outputs. Okay, so tf.reshape is taking some tensors and some other arguments and then returning another tensor. tf.matmul is taking two tensors and providing as output the product of those two tensors made dot matrix multiplication. Uh, that's a tf.matmul. So you can see the operation is so high level, right? If you write it in loops, it's a multiple loops, but over there the operation is a coarse and its single operation is capturing that multiplication, right? And that can be expanded out to loopness, for example, and then you get a form like this. And this is using the affine dialect in MLIR, where these are also operations, but it's just that one operation is nested inside another operation. So the concept of operation is it's basically universal MLR. You have operation takes inputs and then outputs. So in that way, it's actually just pretty printed in this form, but it is also just like it's taking operands, inputs, outputs, and there's something else called arguments. The percentage ij are actually arguments, and so it's still the same data structures, common data structure used to deal with all kinds of operations. Then you get rid of loops. So how do you get rid of loops? You get to straightforward low level control flow where you have a jump there, you execute a body and then increment the counter. You basically a conditional branch. You have or initially have a conditional branch, and then you exit the loop or you execute it, increment, and then come back do the conditional check again. So you have multiple blocks and jump and branches. So that's what you get when you get rid of the loops and go to low level representation. At the low level representation, now you'll start seeing that your instructions are closer to what your hardware executes. And there may be a point where you go to a low level where you have a one-to-one match between the MLR operations and what the hardware has, like load, store, add. And then you can map to that, and then you can generate your assembly from there. Right? So this is the gradual path. Whereas the first thing is like close to a TensorFlow representation, where each node in the graph is like one operation in MLIR. So it's doing many things, that specific operation, the semantics, and then subsequently you can lower it to what are calls, or you can lower it to loopness, and then you can lower it to lower. And the mid-level form is the interesting one for polyhedral optimization. There's a close connection because you have access to loops, multidimensional arrays, and that's where the polyhedral representation comes in. Any questions here? So I've not gone into things like the types that you see here, tensor, memref, and vector. I'll talk about it a little later. So there are operations and there's a type system, and this is just a high level picture. Go into the details of the structure of the IR in the next 10-15 minutes.
There are a couple of questions in the chat, Uday. One question
Yeah.
is
So I'm
Verilog.
not seeing the chat, so please feel free to interrupt me, perhaps after the slide, to just read out the questions. Yes.
So first question is Verilog supported by MLIR? First question. Second question is, can MLIR vectorize a trivial loop implementation? These are the two questions.
Okay, so basically, so Verilog being a hardware description like Verilog or VHDL, you could imagine that there is from MLIR you will have some representation that can generate Verilog. So that's the question you should be asking: is there a way I can use MLIR and do some transformation and then go out of MLIR and generate Verilog, just like people would generate for input? That's a problem that people are actively working on right now. It use MLIR for hardware synthesis, high level synthesis. So you cannot say that Verilog is a different existing language, right? And you can say that you could build something that will take MLIR, lower it to a form where you can from there generate Verilog. So that's so I would recommend take a look at the circuit project, SCIRCT circuit project, with a lot of collaboration, different people, including Xilinx, etc. They're working on the building a dialects in MLIR and supported MLIR to use it for high level synthesis. And I guess the goal, there are lots of different abstractions. It's a completely different ball game when compared to imperative languages and compilation. It requires a lot of different modeling, and so they had to they had to do a lot of design there. And there are lots of other intermediate stages you go through before you get to the Verilog. So there is again a lot of work on this fertile FIR and so they are trying to model that as dialects MLR, and then through a sequence of lowerings and conversions and so on, ultimately you'll get to a form where you can generate VHDL or Verilog, right? And for one of my students is exactly working on that problem also using MLIR for high level synthesis, and the output when you go out of MLIR is actually Verilog. So, but then there's a lot of different modeling that has to be done because uh, everything that I'm going to talk about right now is mostly imperative languages, right? Where you have operations experiencing one after the other, sequential semantics. Whereas hardware, it's all more declarative, descriptive, sort of a concurrent, no sequential ordering for the most part. And so it breaks a lot of the assumptions. And it's interesting, but MLR has the flexibility to model those kind of things also. Right? And this is a completely new, fresh approach. Someone is using these IRs to do hardware synthesis. Okay, the second question on vectorization, again, that's suddenly a question directly diving deep. This is intermediate representation, right? It is not a compiler by itself, right? The MLR is a represent, allow you to represent things, it'll allow you to analyze things, and it'll allow you to transform things. So there are three things: representation, analysis, transformation. I'm talking about the representation. The whole purpose of representation is to make it easy to analyze and transform. Vectorization is one example of a transformation. So if you build a vectorization pass that takes input MLIR and turns it into vectorization, that's a vectorizer. MLIR is right now just core infrastructure IR. You can build all kinds of vectorizers MLIR. So there is already one vectorizer that I, for example, I built out, and it's in my one of my branches. It can vectorize affine loops and turn loops with their bodies into a vector form. A very basic preliminary support. It's not, there is no C++ compiler that currently uses MLIR, right? People are just building the necessary things that they want, and there's a utility to vectorize loops, etc. There are no cost models yet. There's no full-fledged vectorization pass, but you can represent the input and the output uh, thing that you want after vectorization using the operations that are there in MLIR. Okay, so I guess I can move ahead, Suresh. Yeah.
Yes, sure, Uday. Thank you.
Okay, so let's take a look at the structure of MLIR, right? I've just dived a bit, but into the different forms. But how does so MLIR use SSA representation, static single assignment, which is known to be convenient for compiler developers to work with. They're all borrowed from LLVM, but its SSA representation is slightly different from the its equivalent functionally. You can go from one to the other, but different from LLVM. It does not use phi nodes. Instead, it uses basic blocks that take arguments. So both are equivalent. Maybe I'll go into it a little bit. I'll do this a bit later. But it's again, it's a typed intermediate languages. Everything has a type, and you can immediately see the type. So this is a custom form of add. It's saying adding to I32 integers x and x. It's the same as a variable. You get percentage y. This type is I said so. Locally for readability wise, you can see the type of any basically the operands. So SSA variables being used, and you can see the types of function, things like that. This for readability, when you print it out, you can see those types. And so everything has a type. It uses static single assignment, which means there's a single def that reaches all users of that variable. The def dominates all users. You cannot define, once defined, you cannot define it again statically. So that's the static single assignment. And so the def use chains for every use, you statically identify a single operation that is a def or a basic block argument for because there are no phi nodes in MLI. But the basic structure is the following. This is what you need to do. You have a module. Module is a list of functions. Function is a list of blocks. Block is a list of operations. So this is a very restricted view. It's much more general than that, in the sense you can actually even have nested modules, nested functions, MLR allows you to do many things, right? But this is a nice canonical form that you can keep in mind for something like the languages that you know, it compile a C, C plus or whatever. You have a compilation unit, it's a module, and then in the module you have a bunch of functions, and each function has a list of blocks because control flow graph, you have blocks, you basic blocks, and so on, right? Even otherwise, with high level loopness, in that case, you would just have a single block that has everything, right? So that's a block. Block has operations, and operations is the key structure. In MLR, the operation itself can hold other operations in the form of regions. So the list of blocks is called a region. An operation itself can hold a region, which is a list of blocks, and that block itself is a list of operations. That's how for loops, if conditional model, you have basically an operation that holds inside a block, which is itself a list of operations, and so on. Right? So that's how nested loops are modeled in this form. Whereas LLVM did not allow that nesting. It's just list of operations, list of instructions, and then it's a flat list of instructions, right? And then can have multiple blocks, but each block is a list of instructions. But here, MLR operations can have and hold other blocks. Okay. And operation is a key concept. Every operation has a name. It has a source location information. So if you're coming for debugging purposes, for example, when you see GDB entering line number and things like that, right? So this is the location information to propagate operations are forced to have a location information. And so you can trace it back to your original file and line number as to which piece of code actually led to that operation, right? So you have that information, name and source location information. The three things to remember are they have inputs, outputs, and attributes. These are also called inputs are also called operands. So operation takes inputs and returns outputs. Outputs are also called results. So you can have arbitrary number of inputs, SSA operands. So everything's SSA. So each of the inputs is SSA. You have attributes. Anything that is constant, you will try to model using attributes. Right? And then there are region and block arguments, which is the fourth thing. Region and block arguments are things like loop iteration variables, right? This is not neither an input nor an output, but it's saying that execute this block with I going from 0 to whatever. So there are some things that the operation defines. There can be some of the operations can define a region or block arguments. So let's take a look here. You have three operations: the dim, alloc, and affine dot load. So just take a moment to look at uh, these three operations and try to figure out what the syntax is and the semantics. So anything prefixed with a percentage is actually a operand, and they have some custom pre-printed form. So the load operation takes here three operands, X, A, and B, but it's printed in a way such that it's semantically it makes sense to you that the first one is actually the memref. It is like a multi-dimensional memory buffer, and it has two subscripts, percentage A and percentage B. So it's three operands, but with the square brackets, etc. You can tell what is what here. So it is loading from a location percentage A percentage, that's a multi-level subscript, from a 1024 cross 64 memory buffer, that's the logical space, and the name of that buffer is percentage X. Percentage X is being allocated, and so that's the definition, and this is the use. You cannot define percentage X again. So alloc is allocating the memory. So alloc is taking zero operands, returning one result. Load is taking here three operands, returning one result, which is the loaded value. And it depends. It's a variadic number of arguments that load can take. And the memref is the key thing here. Memref is a memory buffer, whereas tensor is a value type. So the whole tensor is like one value. It does not have the notion of memory layout attached to it. But memref, you'll see this is a default form, but there are other forms where you can attach layout maps. It says a row column, a row major, or a column major format, or some other more complex layout, right? And the F32 you see here is a 32-bit floating point value. It's saying that I have 1024 cross 64 elements of type F32. That's the type system. Here is memref, there's tensor, and there's this so the type of percentage Y here, right? And that is just F32. It's loading a single element from that memref. Right? So now you can see what the operands are. Now the question you may ask is, okay, for find load, you can see three operands, one output, alloc, zero operands, giving you the memory of allocating it. The dim is taking percentage one as the operand. So now the question here is what is one? So you have dim percentage one, one. And so the percentage one is a tensor, 1024 cross question mark cross F32. Now, the question mark says it's a dynamically shaped tensor, right? At compile time, you do not know the size only when you allocate it. Not in sorry, tensor is not allocated. It's a value time. There's another way you will get the size, but it's not, the size is not known at compile time. It can be something like n, right? You don't know. So you put a question mark for those that's used in the type. So now you have dim percentage one is percentage one is an input. It is saying get me the dimensionality or the size of the tensor along the dimension one. So dimension starts from 0, 1. Along the second dimension, give me the size of the tensor, and that gives you percentage 2. Right? And here it's not obvious, but percentage 2 itself is of something called the index type, which is this size. So now the question is, what is 1 there? It is neither a input operand, it is not an output. So how do you store that in an operation? Uh, what category would it fall into when you look at the top 5 bullets that I have?
The attributes or attributes, is it? Yes.
Yes, exactly. So that's an attribute. So anything that is constant for the operation that does not change, any property of it that is constant is modeled as an attribute. In this case, the dim, well, this actually changed much later. MLR, now it can be a typical SSA value. Because here you want to find out for this rank tensor, okay, which dimension size are you asking for? And so 0 and 1 or 2 possible. So it's always a constant, right? And so you don't model it as an input operand, model it as an attribute, because it's anything that's compile time constant by design, it's a constant thing. And attributes can be used to store all kind of meta information about the operation. So you define a new op, let's call it some special op. If you want to encode information that you think is always a constant, right? Constant integer or a constant float or a string, which is extremely common, that says, okay, there's some property, right? That can be modeled as an attribute and not as input, because it's not, it is something that you know at compile time, right? It is this string, so it's a constant. So all constants gets modeled as attributes. And you can do all kinds of things, for example, for convolution. Now let's get to like machine learning. Suddenly I'm jumping to high level. It conv 2D, which is a TensorFlow convolution. This is how it's modeled. There's the input feature channels, that would be an operand. Weights is also a input, and the output is the your output basically features, right? Your the whatever the convolution, the outputs computing. So that's percentage out, percentage in. But it has so many attributes, right? You don't model these things as input SSA values, but like saying that, okay, the data format is NHWC, right? And batches, height, width, and channels. It has some dilations. That convolution has a dilated convolution, 1, 2, 3, 1. These are the dilations. There's some padding, and that's the padding specification, which has some semantics. Same means something, valid means something. So that's the ops semantics. You should look at the ops specification to see what they're all encoded as attribute. There's stride. Convolution window is moving, and these are the strides to use. And that's what it's 1, 2, 5, 1, other. So they're all encoded. There's an array attribute. It's not even a single integer, but it's an array of integers. So you can encode a whole lot of information in attributes, and that's how you will encode all the high level ops. Because high level ops, just the input and output won't tell you what it is. They'll always have lots and lots of attributes that give you information. And with this, all this information, now you can say, how can I generate the code for this convolution? Okay? So inputs, outputs, and attributes allow you to model that. So you can imagine any domain that you're working on, right? Say image processing, deep learning. You can define your op by defining what the attributes mean, what the attributes you need, what the inputs and output mean. Okay? So attributes are very powerful and can code a lot. And besides integers, floats, strings, you can also have affine maps. We'll talk about as attributes, which allow you to encode a lot of powerful information in a compact mathematical way, right? And in MLIR, see, every op has parsing, printing, and verification. So if you do some things wrong, it will give you a nice error. So let's say the dilations, instead of 4 dilations, you only provide 2 dilations, right? And you're expecting 4, then the verifier is going to fail and say that this is the inform, right? You don't provide 2 operands, but you provide 1 operand. So there is a parsing, printing infrastructure for all the ops. And for all the new ops that you write, there is a way to automatically generate that with just a declarative specification. And that all is available as part of the core infrastructure. So it may not have the ops that you want. You want to add new things, create new, but the core infrastructure to create these ops automatically generate and emit the printer, parser, verifier are all there. Unless you need something custom, you can always you'll have to add something more. But basic things like to print, and you don't have to write your own parser to parse something like this, right? There is a standard format, and you have to just specify. You can have a declarative specification. Okay, so MLR's SSA representation is slightly, we have probably about 20 minutes. So let me, I'll go through some of the key points here. It's used a functional SSA representation, not an SSA representation that uses fee nodes at merge points. This basically means instead of a fee node, you will have the basic blocks taking arguments. So normally you would have, okay, you have control flow paths meeting, you would get one value from here, other value, and then add a fee node in the traditional SSA representation used in LVM and many other places. But MLS SSA did not use fee nodes because again these are fictitious nodes and they create all kinds of other issues in modeling. Uh, Instead, MLR will use the functional form. Says that okay, from one path you're getting one value x, another path you're getting value y. You will pass that value x from there, pass that value y from the other place, as just like you, as if you're calling a function. You can think of a basic block as a function being called from different places. You pass those different arguments, and you'll receive it as one argument here, percentage x. Right? So BB1 is being given percentage a from here, right? But there's only one person who's calling BB1. However, look at BB2. You're branching to BB2 here and providing percentage W, whereas from here you're branching from BB2 on the top from by using basically, right? From here you're sending percentage B, from here you are sending percentage W. So in some way, percentage Y is receiving either W or B from each of these blocks. And so it is like almost placing a fee node there and selecting from W or B over here. Instead, you would just pass the right value and you'll receive it like a function. And that way you don't have fee nodes. So every use will either have a def or every use can actually be sort of defined via the block argument. So for example, here, percentage Z use has this def here, whereas percentage Y does not have any operation defining it, but it's received as a block argument. So in MLIR, the SSA values are of two types. Either they are the result of an operation, like the output of an operation, or they can be a block argument. So percentage Y is a block argument, percentage X is a block argument, basically percentage here for the input, right? So there are no, this function has an entry block, it has no arguments. So the arguments of the function are the block arguments for the entry block, it has zero arguments. But each block can have some arguments. And when you branch to it, you have to specify which are the what arguments you're passing. Any questions? And everywhere you can see operation, basically the types are all listed. So this operation bar takes zero inputs, no types here. Its output type is I32. So you know that whenever you look at it, read it, you know that the type of, you can see the type locally by just reading the IR, right? It's useful for compiler developers for debugging. Any questions here?
So there is one question now. It is if MLIR is designed to work with LLVM's backend, or is it a completely
I have a figure that I'll explain that. There's a way to lower MLIR to LLVMIR, right?
Okay.
So we can't redo all of it. LLVM has so many backends and so much low-level infrastructure. MLIR does not have low-level back infrastructure like with allocation, instruction scheduling, instruction selection. Instead, you can go out of MLIR, generate LLVMIR, and then they can reuse all of the LLVM infrastructure. That's how they generate code for x86 and all of those things.
Sure.
So it's mostly focus has been on mid-level optimizations, even some low-level, but it's not does not have all the backends. Like the goal is to reuse LLVM from MLIR, you lower to LLVM IR, and then you go through it. Eventually, it can handle everything that LLVM can, and so you could re-implement all of that here, but that will take a long time. And so we just want to see, okay, LLVM is good at these things, let's reuse LLVM for that.
So is there this particular design choice for SSA representation? Does it have any disadvantages in implementing optimizations, or is
So
it?
this is in general, it is known to be a much cleaner representation. Some languages like Swift intermediate language have used this functional SSA representation
Mhm.
instead of fee nodes, because fee nodes, it's the other way around. LLVM used 15 years, has been around 15, 20 years. people have used, and they understand the problems associated with fee nodes and create all kinds of issues. And based on that realization, I think there's a Chris Latner basically chose to use basic block taking arguments for the functional representation for the Swift intermediate language, and that seemed to work out well. And so we adopted that thing for MLIR. So there are some languages, like, yes, Swift intermediate language, some other thing called DLVM, MLTON, which I've used. It comes mostly from the functional programming world. This notion of it's closer to functional form, and basically this has worked better, and whereas the fee node representation has caused all kinds of issues because people take sort of other luxuries with respect to the fee nodes and a license to do other things that it was not meant to do. Like the fee node is it's called fee node because it's a fictitious node. Right? It is just selecting from the tree. It does not really exist in the IR. But people start doing all kind of other things like sub-expression elimination with fee nodes, and basically in some way abused that representation, and it can create all kinds of problems in the sense if you have an error block, everyone is trying to jump to that block, you get a very long list of arguments on the fee node, and a lot of time is spent processing those arguments. Right? So if there is like 100 places, from 100 places you can jump to that piece of code, like something like error handling code, it would get a fee node with 100 arguments, right? Selecting from that and traversing that is in this case with basic blocks. So you would instead have the basic block taking a single argument and it will have 100 predecessors. So there's no way around that. But and then each of that is actually sending one value. In that way, you don't have any fictitious nodes. Right? That's one thing, and you don't have to treat fee as a special thing. Instead, the special thing is the argument. But arguments you anyway have with functions, so it's a more it reduces the number of things that you have to deal with. And one of the interesting things with SSA is that SSA def always dominates all users, but note that the def does not dominate the users in the fee node.
Mhm.
And that's one sort of an anomaly because SSA, the good property, def, all the paths that go to the def will, any paths that go to the users, that reach users has to go to the def. So the def is dominating all users, right? And that's a very nice property, right? And you can whatever value you have there, you will replace all the users at the users. Whereas with the fee node, the thing is that because the fee node is at a merge point, the users in the fee node are not dominated by the depth. So it creates like a slight mismatch or an exception in the definition. Because that thing goes away with the basic block functional representation. Here you will see that all the depths are dominating the users really, is because there's no fee node. And because you're passing this from here, it will have a new name here, percentage by, but it's just that some of the users will not have a def, but the block argument, right, is like the definition. But that's the case with functions. You receive some values in some way. That function which is receiving the values, right, the values that are passed, is defining those values for you. It's getting it from somewhere. So that way, it's a much cleaner and a better representation in all possible ways. That's what people. Uh, that was a conclusion from using all these p notes, and you don't have to deal with fictitious instructions and worry about them. You only have the real operations, right? And block arguments, which arguments is a well-known notion. We anyway need the block arguments for functions. Okay, moving ahead here, since we are basically running out of time, I think I may not be able to finish all the slides that I have, but let me just focus on the more important ones and at least leave 5 minutes for questions. So I should stop in 5 minutes here. So this shows the other aspect where I talked about inputs, outputs, attributes. Here is regions, right? Regions, which can be a list of blocks, how ops can hold. So operations like for, if, while, etc., can be modeled using regions. So here the while operation has two regions, basically the conditional region and the let me just change my mouse here. Yes, this is the operation can hold two regions. This one, the region is a list of blocks. This region has one block, the conditional block. So evaluate the conditional. If true, go to the body, execute the body, and then come back to conditional again. If this is true, execute it again. False, you go back. So it holds two blocks, or it holds two regions. Each is one block, which is again a list of operations. So you have this nesting, right? Similarly, for loops, if loops, you have if has two regions, one for then and one for else, and so you have this hierarchy operations. Right? So this is a different dialect. Operation name has a dialect name dot something. So this is called the MHLO dialect. I've shown you affine dialect. There's a standard dialect in MLIR, and the first you have a prefix for the dialect. the dialect name dot the operation name in that dialect. Right? That's how it's. And so these operations regions are useful to model for loops. For example, this affine for has a single operation which in turn is an affine for that itself has a single block and operation, and that block has one operation which is the few. So you have the nesting for, if, regions, and all kinds of other custom things that you can implement which have hierarchy through basically regions. And this is sort of the list of common dialects used in MLIR. Some of them are outside of MLIR, out of the main tree, but this is how you would go through dialects. I think is your question. So if you want to go from TensorFlow graphs to something like low level, you would progressively lower, and each dialect caters to a specific abstraction level, and it has its own purpose. And so if you have a dialect is basically a set of operations and a set of types that is suited for a specific purpose. So TensorFlow, you would enter through the TensorFlow dialect, which has a one-to-one correspondence to the actual TensorFlow representation in MLR, go through these XLA, HLO dialect, LHLO dialect, these all the machine learning ops. It's and the TensorFlow ops are broken down into these ops. Then you go through some of the dialects, affine, which now the loops start appearing. This is the mid-level. This is where you perform loop transformations. Go to further low level, which is like the kind of things you might have learned in the compiler, like SSA optimization, scalar optimizations, dead code elimination. Things like constant propagation, folding are done throughout, because you could imagine on tensor types also you can do constant propagation, but on the low level optimization like conditional constant propagation, dead code elimination, sub expression elimination, those things would apply on the standard dialect or these low level dialects. This is where you have loops, and then you have standard dialect and so on, and then ultimately you would lower to the LLVM dialect. So this is not the LLVM IR, but it is the LLVM dialect in MLIR. It is still MLIR, but it's modeling or the LLVM representation in the with the MLIR, right? But LLVM IR is a different world. It's a different data structure, it's different IR. But in MLIR, as the exit point to LLVM, you would lower to the LLVM dialect, which models as a one-to-one corresponds to LLVM IR instructions, and from there it's easy to lower to LLVM IR. So you can pick any path, and then you go through these lower dialects, and then go to LLVM, and then you can execute on CPUs and all the backends. So there are other lower level dialects. You'll have typically a dialect for each hardware, modeling the instructions in that hardware. So if you have a new chip, right, you would create a new dialect. And you can always have a mix of dialects. I already shown you an example where it's like affine fur is from the affine dialect. The foo operation, let's say there's a load operation, it's from the standard dialect. So you can have you can mix the dialects as long as the type systems match. Right? The types from returned by one operation being used in other operation. So as long as the semantics match, you can mix different. So let's see here. I think, yeah, I guess the slides are going to be available. I will send those slides to it so you can review some of the other more advanced notions of how to put MLIR. So I've just talked about the representation, right? How do you do something on this representation? How do you transform it? What kind of performance you'll get? But again, MLIR is really IR infrastructure. You can implement the thing that you want and see what you get from it. It is not a compiler that you can just run and get some performance on. Right? It's a IR infrastructure. So I think the rest of this talk, I have some basically talk a little bit more about the affine dialect and the polyhedral notions like affine maps and so on. And then I have like a use case, right? How do you actually use MLIR perhaps to implement something domain specific? How to maybe optimize matrix multiplication using all the infrastructure that's there in MLIR, and how to do that, how to basically implement a highly a state-of-the-art optimization recipe to get close to machine peak performance. And MLR indeed has all the infrastructure in the fine dialect to do that, and how you can get complete performance. So that's what. But all of this could take about at least a half an hour to discuss and explain. But you can should review the slides. There's some also pointers to some papers there which actually show the optimization recipe, and then the slides I just show you basically how uh, yeah, not in a lot of detail, but see how you can actually encode or implement a recipe that does multi-level tiling, packing, copying into contiguous buffers, vectorization, unroll and jam these transformations to get close to peak performance. And again, use MLR affine dialect, load LLVM, and get those, right? So that's what is there in the remaining parts of the slides. And before that, basically, there's some this is explaining. I mentioned about attributes, right? Attributes, you can also have affine maps and integer sets as attributes. That something that MLR uses pervasively, and that's the polyhedral notions in MLR. So, but again, that's I would like I can send these slides and take a look, review those, And there is infinite documentation that is available on the web, right? On the MLR website. There's a tutorial, there's documentation. So I think I would just skip to that part. Let me just go here, right? I'm going to. Uh, so yeah, what are the opportunities available here? Let me talk about. There's a lot of polyhedral infrastructure that was done through a source-to-source compilation. MLI provides a principal intermediate representation. If you're were doing research in this area or doing something, it's and a lot of people are using MLIR. So in terms of the lot of opportunities here and expertise with MLIR is really valued, useful. And any of your existing polyhedral infrastructure, because we are migrating all our infrastructure that was built using this source-to-source stuff into MLIR, because that's a more proper compiler approach, right? That way it will have greater impact because other people in industry or academia are using that, so they can reuse your stuff easily. It is not something that is done and gone, but it can you can contribute it. If you're building new DSLs, new programming models, you can use MLIR to lower it. If you're building new MLI chips, again, this is for the industry, you want to create an MLR backend. So that way you get support from all the programming models because all programming models are going to load MLR. So if you have backend for MLR, then it means all programming models will run on your hardware. It's similarly, if you build a lowering framework into MLR, if you have a new programming model, then it means anything that can handle MLR is able to run your programming model. So both ways, that's useful. So that's why there are opportunities. And if you are basically, so the conclusions here, I think based on what I said, is yeah, so MLR is providing IR infrastructure that can lower compute graphs because this is what a lot of MLI program models are using to high performance code provides you a single representation to reason about both high level and low level. The lowering is progressive in the sense you're not discarding any information suddenly. You have a way to represent all the different forms, so you can lower your computation basically in a progressive way, in small steps. Right? The abstraction changes not suddenly from a high level form. You directly go to a low level control flow graphs where all the information on the operation is lost. So here with attributes, with the loop level form, with all the modeling that's there, you can model it at different levels. Right? And this allows you to share infrastructure across both general purpose compilation and domain specific compilation. Everyone uses MLIR, they're reusing the same infrastructure. If you're doing compilation for deep learning, image classifier, you would still use the same unroll jamming utility that someone is using for C compilation, right? So that way you're not duplicating the same thing. So that way I would say that IR infrastructure should be one. Compilers can be N, but you have single IR infrastructure, open source, reusable, then that really saves a lot of time and costs, right? And then the other thing is besides domain specific and general purpose, just like MLR unifies the infrastructure or provides a unified it sort of unifies the paths for domain specific and general purpose compilation by providing a single infrastructure that can serve both needs. Similarly, these libraries and compilers can also coexist. A lot of the deep learning revolution has been because of highly tuned handwritten libraries, right? They're not things that compiler automatically optimizes and generates, but they're all hand tuned. But they're all hand tuned with C, inline assembly, and so on. But if they use IR infrastructure, then that approach can become more modular, reusable, and you can automate generation of libraries because MLR has all the necessary passes, utilities, and instead of using hardcore doing that by hand, you can use the same infrastructure that the general purpose compiler that the compiler is using. Compilers with Unroll Lam, normally they would do everything by hand vectorization. Instead, use these IR utilities. It's extensible, flexible enough. As a you can define your own ops that you can instead of trying to do that by hand, you can reuse the existing utilities, the same utilities that compilers or code generators would use. You can actually, if it's domain specific, so you can think of generating those libraries, right? You can generate, let's say, library for doing matrix multiplication by putting together exactly the choices or the transformations that you want, as opposed to letting the compiler doing something automatically in a generic way. Right? That way, both library generation can be using the same infrastructure. Right? So that's sort of a unification of all of these different kinds of optimization work here. And if you're interested, yes, as I said, take a look at MLR is being developed as a sub project in the LLVM. So the repository for MLR is the LLVM repository. So if you check it out, you'll see a folder for MLR. So that's where it is. There is the infinite documentation, lots of basically talks which have slides, recordings, so on in the Open Design Meeting. They're all available publicly. Go to mlr.llvm.org here. So let's see here. Right, so this is the, let me get the pencil here. Just trying to get the 1 second. Yeah, so mlr.llvm.org is the place where you'll find all of this stuff. This is also a tutorial that you can try out. And again, the best way to learn these things is to try the code out, right? Build it, try to implement something, go through the tutorial, go through the documentation, and some of the slides and the video recording available. There are like lots and lots of talks on that are linked. And obviously, if you're close to graduation, there are a lot of opportunities here. A lot of companies uh, are looking for MLAI compiler engineers, and MLR is the infrastructure that can be that can be a really valuable skill, because getting used to it is it takes time, right? And as a student, if you are doing some project with it, that will provide you a valuable skill for the industry where there are lots of opportunities. And then obviously, even if you're trying to do a master's, PhD, it can serve as the basic infrastructure to test, implement your whatever new thing that you're planning to propose. If you're doing a if you're doing a systems PhD, even in MLAI systems or even general compiler systems, that can be used as the vehicle to implement, design, evaluate any new framework that you're building, whether it's a compiler or optimizer or a new language or any other thing. It's because it's going to last, right? If you implement in MLIR, so it's also good for academic collaboration and for obviously for research. Right? That's the thing. So yeah, so I think with this I'll conclude. I guess I can take any questions.
Thanks a lot, Uday. So, if you have any questions, you can either put it in the chat box or you can unmute yourself and ask. There is one question immediately that is there in the chat box, that is, where can I find the procedure to lower HLS or OpenCL ML code to MLIR?
Yeah, so just follow the you're saying OpenCL.
Or HLS, lowering HLS or OpenCL to.
No, but these are very two different things, right? HLS is high level synthesis.
Mm.
OpenCL is a accelerator programming model. uh, there's no OpenCL. There's basically there is some work on SPEAR-V where you have say intermediate representation tied to accelerators. Say there's a way to lower MLR to that, but there is no as far as I'm aware, there's no OpenCL front end yet for MLR. So again, I would suggest not trying to use something. Think of using MLIR for just as a user, but think of it in terms of looking at opportunities where you can contribute to it and build it out if it's not there, as opposed to just using MLR to get some optimal, because it's a IR infrastructure, and if it's not there, you can basically build it, but not to think in terms in terms of just using it as some black box to do something. So HLS, I would suggest taking a look at the circuit project. It is too early. They're building many things out. So CIRCT, that's the project that I would recommend looking at. Basically, uh, that's it's being driven mostly by some university teams from Xilinx, and then some team from Sci-Fi and so on, and a lot of community. So you can follow the design discussions there. And so it is not something that is there's no finished product for you to directly use right now, but perhaps in a year or so there may be something more mature to do HLS with MLIR, but it's an active sort of development. Right? OpenCL, there is no, as far as I know, there's no OpenCL front end that lowers to MLIR. There is a SPEAR-V backend in MLIR.
There is one more question. Has PyTorch adopted MLIR or they still using their own native IR?
They are still using their own native IRs. PyTorch has not adopted MLIR, but however, there are some efforts to, there's a path from Onyx to MLIR, and PyTorch can be converted to Onyx and MLIR. That's one path. The other path is PyTorch has a path to XLA, that is the XLA proper, right? So PyTorch to XLA, and from XLA you can import into MLIR. XLA protobuf or XLA representation can be imported. So there are two paths, right? So, but the more mature path is PyTorch XLA can go into MLIR. That's one way to get PyTorch MLIR. Not everything may work. Whereas the Onyx thing is slightly less mature. PyTorch can be exported to Onyx, I believe, and then Onyx, there's a Onyx dialect in MLIR. That would be the entry point at MLIR. So it's some simple PyTorch models. You can actually get them into MLIR that way.
So with all this, Uday, like where does GCC stand? Because GCC serves a totally different purpose in the current scenario, or
So basically, GCC infrastructure, right? So there's LLVM and GCC infrastructure. Uh, it's again, GCC infrastructure is mainly not designed, or they're not. I don't see any effort there to make it add abstractions for domain-specific compilations, MLI compilations. So as such, people would just prefer LLVM to GCC even for the low-level things, right?
hmm.
And I guess someone suggested GCC could actually migrate its intermediate representation to something like MLR. They should take a look, but that's like a lot of effort. And again, it's mostly catering to more general-purpose languages, lower-level things for which a low-level representation is needed. Of course, Americans serve that needs, but there's not much. Of course, I think the people pointed out that maybe they could use MLR for some of the GCC's intermediate representation for the future, but it is still a more is a representation infrastructure for lower level things, C, C++, Fortran, those kind of languages, and mainly quite important because it handles large number of targets which LLVM, not even LLVM handles, right? LLVM still can't compile the Linux kernel. It's not yet there, but because this is just supports so many things, all kinds of weird hardware also. So for all of them, GCC is still the infrastructure, and it will take a long time for even LLVM to replace something like the GCC, even if it's better in many ways, right? So that way it's going to be there, right? And but it doesn't. The intermediate representation, it does not have the kind of flexibility, abstraction, modularity, reusability, even on par with LLVM. And this is MLR is even a step further, right? It's aimed at all these new abstractions and the future programming languages. And it's hard to change the IR for anything because it's a big undertaking to redo everything with a new IR, something like CC.
so why can't LLVM compile Linux kernel, for example? Is there
Basically, because the kernel code, again, I'm not knowledgeable on this one. Someone actually tried to do this was a big effort. So people have managed to compile it. The team at Google managed to compile the Linux kernel finally. LLVM and actually get it working with some, I think, caveats, but after a big, sort of a huge process, right? Because I think the code, Linux kernel code, the C code probably makes certain assumptions, and then also it's just that the standards, right? The assumptions that it makes on C and the patterns that it uses maybe is not in line with some of the assumptions that LVM makes. And so, for example, with a lot of effort, someone managed to just get it compiled, right? First of all, it doesn't even compile, so let alone running and booting. But I believe it could not compile the code, runs into some errors in the compilation itself because it has some expectations and maybe the practice does not match the standard. I think you can find it more online. But someone finally managed to change LVM and with all kinds of things, Clang, right? It's not LVM, but Clang compiler, and then managed to compile it. But then after compiling, it didn't boot or whatever, right? Because it miscompiled it. Right? These people may use all kinds of weird patterns. It's low-level systems programming, right? So that's where these differences may crop in. And but I think this team that managed to just do that, but making changes to the upstream to get all of that is still a lot of but as an experiment and with a lot of local changes they managed to do that, right? So because again I think it's mostly low level C system programming, making certain assumptions that LLVM as a compiler does not support. For that matter, I don't think there's any other compiler that can. I'm not sure if let's say Visual Studio C++ compiler can also compile the Linux kernel. I think GCC is still the thing that is used to compile all of these things, right? For like what are Linux distributions, the kernel, and all the packages that we use on Linux machine, and they're all GCC compiled. Right? So other compilers for the low-level stuff, they're still not there.
So maybe one last question, Uday. So there is this question, PyTorch has a dynamic graph representation, while TensorFlow uses a static graph. How much this matter while trying to use MLIR to represent both? This question is from student
Oh,
Prajwal.
that is a old. So that TensorFlow representative was an old TF1. TF2, the eager mode is the default. So it's closer to the PyTorch representation. Earlier, it was a what they call a define then run, whereas the PyTorch was define by run. That is, the graph is what you don't construct the graph and then try to execute it, but as you execute it, the graph is being constructed. So that's the TensorFlow eager mode. So they had the original the graph mode, which was deemed to be good for performance, but for programmability, the eager mode was better. They introduced the eager mode, and TF2.x, I believe you can again check it online. I'm not an expert on this one. The eager mode was made the default, so they're moving in the PyTorch direction, right? The eager mode is still perhaps evolving, has to get better, but the eager mode is the default one. So it is again the define by run interface as opposed to define and then run, which is the static graph mode. So, and how it impacts, yes, so it has an impact on not just MLR or whatever intermediate representations, whatever compilation you're doing, because if you just construct a graph and then, yeah, that's, you can take a look at the graph, then lower the graph using MLIR, that's one thing. But the dynamic execution, that has to be, if you want to do like a JIT compilation, that has separate implications on how you actually build out things like a fusion of different nodes in the graph, right? If you're already given a graph, you'll optimize the graph by doing this fusion, that fusion. It's already given to you. But if it's dynamically done, how do you actually do? It's more of a dynamic compilation problem. What impact does it have? It's a good question. I don't have a clear answer right now, but it's something that requires in-depth investigation to see how things are done right now and what role actually compilers have to play in that sort of a settings. If this is same piece of code is executing multiple times, people have done JIT compilation, identified hotspot, optimize that code away, right? And so in that way, it's also similar to Python. How would you use MLR to do Python JIT compilation? I should take a look at the NPComp project, NPCOMP, which is Google. There's a team there that's trying to use a NumPy-like abstraction to actually use MLIR for its optimization, right? So that way, not dynamic. So, but yeah, that's a big undertaking how to use MLIR for PyTorch in a general way. And I think there's no, so far, I think most of the people are focusing TensorFlow, MLIR, but I think in the future, if there are good results with this, and it makes sense for other programming models to move to MLIR.
Nice. Thanks a lot today. I think we can conclude today's session with this. Um, yeah. So
Yeah, okay. So thank you again for the questions, and I will send the slides to Suresh and review the slides. But more than this, you'll find information on the web, and do try out, and the contributions are welcome. But do make sure that before you post on the forum, the thing, review all the material. There's a lot of documentation. It does take a lot of time. So go through the tutorial if you're interested, and try the code out. Right? Uh, it's that way you would learn more than just by reading slides and papers.
sure, Uday. Thank you again. Have a great day. So
Yeah,
sure.
thank you. Bye.
Yeah. Thank you. Bye. Thank you, everyone. Bye.